Could you hear me before? Okay, but then, okay. Hi, so I'm going to tell you about focal conics today, and I'm flattered actually to speak after Maurice and to paraphrase Newton. We've only seen as much as we've seen about focal conics by standing on Maurice's shoulders, which is why he had to have back surgery a few years ago. So let me start. Is it possible to turn off this bright light? Testing, sound check. It's like a Nick Park video. This light. Okay, anyhow. So we get to study these beautiful things, and you already saw pictures. These are these beautiful ellipses, and there are hyperbola, and there's even parabola here. And I'd like to explain all these things to you. And let me start by writing down an energy, because energy is important to people. And so there's a free energy to describe smectics. And I'm going to talk only about smectics today.
What does the title mean?
Reine und angewandte means pure and applied. The only language where pure and applied go together. Okay. So they have many journals called that, right? So anyhow, here's a smectic, okay? And the smectic is this layered system, and you can think of it as being neat, made out of little ellipsoidal molecules with little oily tails, or if you like, you can think of them as lipid bilayers, right, where you have these oily tails and these charged heads, and there's water in between. But from my point of view, a smectic is some kind of density wave. And so we're going to start by talking about the density wave as level sets of some field phi. So I'm going to describe my layers as level sets, and what's cool about that is by describing them as level sets, they never intersect, right? Phi equals 0 and phi equals a and phi equals 2a don't intersect, so I already built that in. I can turn that into a density. That's the thing that one might scatter X-rays off of, or neutrons, or whatever, even electrons. Okay, and so you have some density wave, which is cosine 2 pi phi over a. So you see wherever there's a peak in the density, that's the same thing as these level sets phi. I can write down the layer normal using standard electromagnetism, right, or electromagnetic theory, or whatever you want to call it, right, grad phi over its magnitude. And it's typical, if you read Landau and Lifshitz or Chaikin et al., they'll tell you things about writing things in terms of this phonon field U, right? And so usually you decompose phi as z minus u. If u were 0, then you just get a nice wave going up the z-axis. That's the standard coordinate. We always have it go up along z. And u then is this Eulerian displacement field. And I can write down some free energy, and I don't really care about the free energy. All I care about for now is that the free energy is rotationally invariant. By making it I make it rotationally invariant by writing it manifestly in rotationally invariant way. So gradient of phi squared minus 1. You know, there's a long story. There's a song and dance about where this nonlinear term comes from, say in Landau and Lifshitz. But it just comes from expanding this. Grad phi squared minus 1 is nice and rotationally invariant, as is the mean curvature of the layers, which you guys have divergence of n. And I don't want to talk about this anymore. I want to talk about phi alone. Okay? So the nice thing about smectics in 2 dimensions is that there are enough dimensions to draw everything. Okay, and so what I'm going to show you here is I'm going to address some of the points that Maurice brought up about the integrability conditions, about dislocations and disclinations in material. So here's phi, here's the xy plane. If I had a 2-dimensional smectic living in the xy plane, I can write this function phi as a graph over the xy plane. This is not the smectic layer. It's just a green surface. Okay? All right, it's a green surface. It has nothing to do with the smectic except that now, when I say that word level set, I really mean level set. I take the level phi equals 0. It cuts through the green surface. It makes a curve, which I project out on the xy plane. And I do it again for phi equals 1, and phi equals 2, and 3, and 4, and so forth. And you see that I can look at the level sets of this green surface as the smectic layers, which is what I just told you I was doing. So you say, oh, is that good for anything? It's a nice picture. It's excellent, because what it makes you realize is that smectics, see, smectics, are really topographical maps. Topographical maps encode all smecticness in them. For instance, the lines don't end and the lines don't cross. 3,000 feet and 4,000 feet never cross. Or how would you say it here? 1,000 meters and 1,237 meters don't cross. You can see why the English units are better than metric. Right? They're nice and round, 1,000 feet, 2,000 feet. Okay? So here are the layers, and you can ask yourself, right, here's my layers, and so this already gives me something periodic, right? So here are the periodic structures. We're going to talk later about equally spaced ones, isometric embeddings, but here are the layers, and then you can look at this Mount Rainier here, and you could say, how do I know if I'm at the top? Well, you know if you're at the top, if every way you look down, if every way you look is down. Here, see, down, down. All right? So that means that you have a place where the contour lines go around you, because you're at some height and all the other contour lines near you are lower than you. And so these lines, these contours, these critical points of the map, these are precisely where the +1 defects are. You see the disclination? You see how the director goes around those +1 disclinations? Of course, if it's a smectic, I don't get to put an SIGN on these numbers, so it could be that it's a basin. It could be the bottom of a lake or the top of a mountain. You can't tell from the contour map without the numbers. And you say, well, Maurice mentioned that you can't always have, when you have systems with translational order, you can't have any kind of defects you like. There's some extra integrability condition. So let me think about it. Here's a +1, here's a +1. Suppose I try to add the two +1s together by bringing them closer to each other, which you can do in a nematic. People do it all the time. They bring the defect lines, the point defects together. You get a +2 defect. You can bring 3 of them together. You get a +3 defect. Well, the problem is that there's always these mountain passes in between the mountains. In fact, there's a theorem, the mountain pass theorem, that says there's always a pass between the mountains, right? And if I try to bring the two mountains together, I always trap the pass, right? In other words, you can't put a mountain on top of a mountain, yes? What's it mean, right? You can't put a mountain on top of a mountain. What they do in the United States is they cut the tops of the two mountains off, and they make the whole thing into a plateau, right? Well, that's in the western United States. Where I grew up in the Midwest, they fill in that gap with trash, right? Generated in New York City. And so they fill it in. And really, who's from the Midwest? Anybody? Anybody? Right? Mount Trashmore, right? Mount Trashmore. There's many places called Mount Trashmore, which are old hunks of trash, right? Exactly, exactly. All of Staten Island, my understanding, is made of that. So what happens is you always trap a pass. And look at a pass. A pass is actually a -1 disclination. So if you try to bring two +1s together, you always trap a -1 with you. And so you can't actually make a +2 point defect. You can't put a mountain on a mountain. However, if you're lucky and very fancy, you can arrange things so that there's a magical mountain pass that goes around 3 mountains. John, do you know the name of one?
Triple divide. No, there's a triple divide.
Electric Pass. Electric Pass near Aspen is a place where there's 3 valleys, right? And where you can also get, it's very high, you can get electrocuted. It's even harder to get to than that lake. Okay? So there's Electric Pass. You can have a situation where you have negative defects of any charge you like, but you can't have positive defects. And so there's this theorem by Ponaru. So it's a real theorem proved by a real mathematician in a real math journal. All right. Here you have this +1 disclination. You can have a half. You can have nothing. You can have -1/2, -1, -3 halves. He said this thing about measured foliation or something. Or does he have a word like that? Measured, yes, a measured foliation. The point is that if you want to actually continue to have layers, you cannot have any defect beyond +1. And he proved that, and I just explained it to you in terms of these mountains. So it's a very nice mapping to think about the smectic as just level sets or a topographical map, and it explains this theorem nicely. So that is one way of approaching this. Now you say, well, I've introduced all this extra technology. Ponaru knew Morse theory also. His argument was really rigorous. Our argument was just a picture. How can a picture be rigorous? But the picture is useful for other things. I want to convince you that that's the case. So here's my energy again. Let me say something about energy, which is kind of a funny thing. So this is a nonlinear energy. It's highly nonlinear. There's no, what's that word? There's There's no adjective for amount of nonlinear, right? It's nonlinear. It's nonlinear. Sorry?
Non-linearity.
Very nonlinear, especially nonlinear, uniquely nonlinear, highly nonlinear. It's nonlinear, okay? So when you have a nonlinear elasticity, the problem is we can all write down different nonlinear elasticities. For instance, you notice I only wrote things down quadratic in this nonlinear strain field and this nonlinear bending. But you can write down quartic terms. Nothing forbids you. I mean, there are quartic terms, right? And the quartic terms are also nonlinear. They're even more nonlinear, or they're nonlinear in nonlinear quantities, okay? And so what can we all agree upon? We can all agree upon the quadratic theory. We can all agree upon what Goldstone's theorem forces us to agree upon, that there has to be some low energy modes, there's some quadratic expansion in some kind of phonon field, which represents a spatially varying version of the global translational symmetry, and we can all agree that this is the theory of smectics for small displacements. This is what you'd look up if you looked in Landau and Lifshitz. Is it volume 9? Volume 7? 7. It's very good. It's a quick read. Not an easy read, but it's a quick read, right? And so this is what you get. You get a bulk modulus, you get lambda, which is some kind of penetration depth, the ratio of a bend modulus to the compression modulus, and that's the theory. So I'm going to say the following thing. Any nonlinear theory that has this as its quadratic limit is a perfectly good explanation of the smectic, because eventually we always truncate at nonlinear order. We have quartic terms, higher order terms in all the strain fields. Whatever theory you write down, right? I'll write my theory down. Mine will be a nonlinear transformation from yours, but they'll all be nonlinear. But we'll all have to agree on this. In other words, when an experimentalist measures things, experimentalists can always measure b and lambda squared unambiguously. But as soon as they measure non-harmonic terms in the free energy, they have to tell you which free energy they're talking about. Yes, Vincenzo. You should identify yourself. Vincenzo Vitelli, Leiden University. Yes?
But an experimentalist presumably could measure some strongly deformed textures.
Vincenzo says an experimentalist could presumably measure highly deformed textures. Yes, and if they took those highly deformed textures and tried to back out elastic constants, they would have to pick which nonlinear elasticity they were going to do.
Yeah.
Exactly. But we'd all agree on these terms, okay?
Actually, there's one comment, which is that the leading order next nonlinearity is also fixed by the symmetries force, as you know.
What does that mean?
The leading cubic nonlinearity, the dzu grad curve u squared term, its coefficient is b, up to a factor of 2.
That's right. I agree.
So Randy, can you go a little bit?
Yes, John says that symmetry, rotational symmetry, dictates that the cubic term, if you expand in powers of u, is also set, right? But I would say that, I guess I'm thinking of this as the whole strain. This is the whole strain field, right? So, okay. So, what I'm going to do is I'm going to write down a different free energy. I'm going to write down a different nonlinear free energy. This is the standard one. I'm going to write down a different one. It'll be okay. We're going to agree to quadratic order, right? And my nonlinear theory is a nonlinear transformation of your nonlinear theory.
And it's also going to be rotational.
The whole thing, the full catastrophe. It'll be rotationally invariant, but it's going to be much more geometric. So what I'm going to say is, remember that green surface that I told you wasn't really there? Well, let me just imagine it is there. Here's the normal. This is the normal to the green surface, right? Phi is the height function. This is the unit normal to that green surface. Okay? Because it lives in 3 dimensions. And here's some math, if you like. The point is that I can rewrite that entire free energy in terms of the divergence of this normal. The divergence of the layer normal, the normal to that green surface, is to the same order, to quadratic order, the same as the divergence of the smectic, of the pneumatic director in the smectic. Everyone get it? This lives in 2 dimensions. This lives in 3 dimensions. Its 3-dimensional divergence squared to the same order is the same as its 2-dimensional divergence squared. That's good. The other thing is I can write the compression term, the bulk modulus, as just saying that n wants to point in a particular direction relative to the z-axis. The green surface lives up and down the z-axis. In other words, if I want to have equal spacing, I want to have a surface like this. Right? This mountain range, see this one, has equally spaced layers if I took level sets. So this is just telling me that the normal wants to be like at 45 degrees to the z-axis. By the way, if you want to be fancy, this is just a convention, which is the same as setting the speed of light equal to 1. I'll make that clear by the end of the talk. So here I've written down a new free energy. Look how cool this one is. This one is not an integral over space. This is an integral over this surface, the actual surface. Here is this bending term. This is the mean curvature of that green surface squared. If I didn't have the compression term at all, this is called the Willmore problem. And you fix the topology of the surface, which essentially means fixing the sets of dislocations in the surface. And you can then minimize h squared subject to this constraint. And then there's this extra piece, which is like a field that's telling me the normal wants to point in a particular direction. So it's rotationally invariant in the xy plane.
Randy, so H is the curvature of the three-dimensional, so the Gaussian curvature.
The mean curvature. H is the mean curvature. He says, so H is the mean curvature. He said, Randy, H is the curvature of the three-dimensional surface. I said, yes. He said, the Gaussian curvature. I said, no, the mean curvature. They asked me to repeat the questions. Okay, that wasn't a question, but okay. So anyhow, I'll still repeat it. So here's the problem. So here's the theory. But this is very elegant to write it like this, and I'll show you why. By rewriting it in this nonlinear way, it makes solving a certain set of problems very easy. Because now I'm thinking of the normal to the green surface. That's sort of my variable that's interesting to me, right? This energy, this is the divergence of its normal. This is the normal. This is a theory in terms of the surface normal. So if the green surface wants to be equally spaced, in other words, if I want this to be 0, how do I make it 0? N, big N, has to always be at 45 degrees to the z-axis. So you know what's cool about that? Here, you have this curve, the Tropic of Toner. He lives at 45 degrees north, okay? And here you are, and because you told me in Aspen 1.5 years ago. Okay. He said, how did I know that? So here you go. Here's this circle. All right. In fact, 45 degrees north is defined by where John lives. Right? Just like Greenwich Mean Time. Right? Okay. So here's 45 degrees north. The cool thing is if I want to have a surface, a smectic, a two-dimensional smectic, it means that its green surface, which isn't the smectic, it's just that green surface, has to have its normal always pointing at 45 degrees. So its normal always lives on this curve, right? Well, you know what's cool about that? The area swept out by this normal is precisely the Gaussian curvature of the green surface. That's, you know, the whole point of the Gauss map. And since this curve, this vector always sweeps out a curve and does not sweep out any area on the Gauss map, the Gaussian curvature must be 0. And that's so constraining in 2 dimensions that it tells me that it has to be isometric to the plane. And being isometric to the plane gives me one of 3 surfaces. If I want to have constant tilt and flat, I can have cones, I can have planes, or I can have cones attached to planes. All right? There's actually a 4th surface. We call it Nistor's surface, which I won't tell you about. But actually, Nistor's surface has this beautiful connection to the evolutes that Maurice was talking about. There's a very nice, elegant connection, but I don't have time to talk about that. So and here are the structures. So unlike things that were said at meetings that I can't say anything about, I have just proven to you that these are the only 3 textures that can be equally spaced. It would be impossible to take something that was a -1 disclination in 2 dimensions and construct an equally spaced thing without introducing cusp lines. So when I say without, I mean these are the things I can draw as long as the layers are nice and smooth, have no cusps. So that's kind of a nice result. -1 defects cannot be equally spaced unless you also have focal lines. So focal lines, I let the cat out of the bag. Right? First of all, I mentioned this at the beginning. When I talked about the topographical maps, I said you can't tell a basin from a peak in a smectic. That's because there's this extra symmetry. The smectic has this up-down symmetry. And so let me tell you what that means. So I had that surface. Remember the surface, the green surface? All right. First of all, the green surface is level sets of phi. Of course, the density that anybody measures is cosine of 2 pi phi. That means that phi and phi plus 1 in these units are exactly the same. So for one thing, I can take that green surface and translate it up by 1, or down by 1, or up by 3, or down by 7, or any integer I like, and it's the same smectic. So that green surface already doesn't actually live in R, it lives on the circle, and I can repeat it periodically. In fact, here's a clever thing. Instead of taking level sets of one surface, I can take the green surface and do all its translates, and then I can take one slice, right? Because phi equals 0 for surface 1 is the same as phi equals 1 for surface 2, which is the same as phi equals 2 for surface 3. So I actually can just copy the surface over and over again and take one slice. But then there's this extra thing, this phi goes to minus phi symmetry. So remember the ground state? You guys nodded. Remember nodding? You nodded when I said it. I showed you this. I saw you guys nod. Yeah, I went like this. Yes, okay. So here's the ground state. Here are the level sets. Okay. Here's another level set. Like I said, here's another one that does exactly the same thing. And I could take a slice like this. If I copied all of them, I could take one slice at one height and get everything. But because I can't tell up from down, in a smectic, I can also have these surfaces. The red surfaces give me the same ground state. However, so that this density is single valued, the red and the blue always have to cross at special places. So there's going to be an extra little constraint about how the red things and the blue things cross, where they cross. But basically, I have this whole egg carton construction of the smectic ground state. So the smectic ground state is a set of parallel red layers and a set of parallel blue layers, and they're perpendicular to each other, and they intersect at only special places, and they go on forever. And I can take one slice at one of the special heights, at the integer heights or half integer heights, and I will get my smectic ground state. And if I pick some other height to do the cutting at, I'll get nonsense, because I'll get a different answer for the red surfaces and the blue surfaces. Okay. So you have to be careful if you want to do this correctly. So let me draw a picture for you of a plus 1/2 disclination. You see? Plus 1/2. So here we go. You ready? All right. I'm building it. There. You see how I have a piece of cone attached to a flat surface? This is equal spacing. Right? This happens to be an equal spacing structure. It goes through itself like so. So if you look at this surface, there's this line here where the surface crosses itself, but don't let that worry you. That's the line. By having the line cross exactly at that height, I always get one answer. It's single valued in terms of the density field. And so I have this cone, and they're attached to these surfaces. But you can do magic if you like. You can try to follow what the normal to the surface is, and you'll discover that this surface is not orientable because it crosses through itself. All right? And that's the same non-orientability as the two-dimensional smectic, now promoted to 3 dimensions. What about the minus 1/2 disclination? So it looks like this. Here we go. Look at this. I'm building up. Ready? Ready? Bam. Okay? They intersect on this line. And I keep going. You see how cool it is? A disclination. Phi equals plus 1, which is the top edge, and phi equals minus 1, which is the bottom edge, give you the same curve. Because that's what a disclination messes up and down, and messes up phi and minus phi. So let's do a little gymnastics. I'm going to respond to Vincenzo's question, which he asked, which promoted this whole problem. But go ahead, ask your question.
Well, maybe one at a time.
Okay, well, you already asked one 4 years ago. Now what do you want to ask?
I was just wondering if you allow a little bit of stretching of the layers,
Yeah.
maybe because that bank term is not 0. You have to trade off a bit of the two.
Yes?
How would this universal shape change? Is there a class of smooth deformation of the shapes that account for?
Okay. Vincenzo says, suppose that you added a little stretching, a little deformation, so that the things can be spaced a little differently. I have to get the whole part, the whole question. How would that change this problem? I say, it would change it. It would make it harder. I'm looking about those surfaces that are equally spaced right now, okay? All right, you'll see. Otherwise, the word isometric won't come in.
Is there a sense that maybe those sharp joints would be smoothed out?
Is there some sense that the sharp joints would be smoothed out? What? Yes, of course they would. Okay. It's a hard problem, though, because it's highly nonlinear. Okay.
No, I wouldn't say that. I would say that what you're doing now is to focus on the strongly nonlinear part, and you want to put the linear one as a small perturbation.
The small perturbation is tragically not linear. Let me just add to that, if I might. As you know, Vincenzo, if I take a screw dislocation in a quadratic smectic, the energy is 0. And if I take a screw dislocation in a nonlinear smectic, the energy is infinite. So it's hard to say that the nonlinear theory is a perturbation around linear theory. I mean, you know, you could say it. Okay. Anyhow, here's the -1/2. So let me tell you about this cool thing, which bothered me a lot when I've read papers on this, is here is the pinch, or the pansement. It turns out pansement is no longer French. We published a paper. We tried to put it in italics so that it would be French, but they said, no, it's English now. It has something to do with your intestines. You can, if you eat two magnets and they go on opposite parts of your intestine, that's called a pincement in English. Okay. Anyhow, here's the pinch. You take a bunch of layers. You see what you can do. You can just retract this +1/2 into this -1/2 disclination, and everything goes away. This is very bothersome because I grew up learning that a disclination dipole is a dislocation, but not here. Okay? So let me show you the pinch in my three-dimensional language, right? So here's the pinch from a top view. Here, I'm turning it sideways for you. So here's this -1/2 attached to a +1/2. You can see how I can just pull this guy up like so, right? And in fact, I can separate them into a +1/2 and a -1/2. But then you have a dislocation, which is also a disclination dipole. And like, what the heck? Is it disclination dipole? Didn't it bother you that people would say a disclination dipole had a charge when in fact it shouldn't have a charge? Because you know, it's a plus and a minus. It should cancel. So I just showed you a version where it cancels. Now I'm showing you a version where it doesn't cancel. This actually is a dislocation. Look, do you see? Here's the -1/2 and here's the +1/2, and the -1/2 hugs the +1/2. But when I turn it sideways, you see the difference. The difference is that to get the +1/2 and the -1/2 to join up in the dislocation, they have to be at different heights. They were at the same height in the last picture. Now they're at different heights. There's an offset. And I told you that these lines where the surfaces cross are forced to be at certain heights, or your density wave is not well defined. That means I'm not allowed to deform things to move those crossing lines. The crossing lines can't move up and down. As soon as they move up and down, they mess everything up. So they have to stay where they are. So there's no way to get this red guy up half a spacing in this direction. And because of that, I can't turn a dislocation into a disclination. And it has to do with how you hook the things together. So it's an integrability condition, but now represented in this geometric way. And see, I can separate them. All right? But there's a different height. I'll never forget when Brian Chen explained this to me. He went like this. I said, that was brilliant. Right? Remember, right? That's all it is. Okay? You can do that at home. All right. So, and of course, you can then put them together, and I can take cuts through it. Watch this. Here's cuts, right? And there, you see, we hook together disclinations of the two charges, and we get the dislocations, like so. And I want to just add back, hold on. There's two geometries. There's this geometry of a +1 dislocation. I'm sorry, there's this geometry, and there's this geometry, and they're continuously related to each other in this space. Okay? And you see when I take a cut at the wrong height, how I get this stupid stuff? I have to take the cut at the right height, at the half or whole integers. Okay. So, I have a lot of time. Okay. So let me go to focal conics, because we saw these pictures. This, just so you appreciate how cool this picture is, this picture was taken on a second-hand Motorola Razr phone, circa 2002 technology, on its little digital camera in Boulder, Colorado by Gareth Alexander. Everybody give Gareth a round of applause. Okay, it's excellent experimental work. So in other words, this is really easy to see. This is a tube of smectic that's been sitting in Boulder, Colorado for 38 years, just sitting and resting, okay, and forming these beautiful focal conics, these perfect ellipses. It's amazing. All right, how can anything be so perfect yet so messed up? It's not the ground state. All right. Here's some nicer pictures, right? And let me try to explain where they come from. So imagine you have these two cones. Remember, cones, here's my three-dimensional picture. This is the smectic. This is my green surface. It's blue now. But that's just a thing about an observer. Oh, I was on this thesis defense. This is being video. This is being streamed live, but it's early in the morning. I was on this thesis defense. We were having discussions about special relativity, and we realized that there's a difference. You have different kinds of observers. There are the observers who understand special relativity, and the observers who don't understand special relativity. So they're always going to disagree on what they see. Anyhow, here are these two cones. This is the surface, all right? Anyone remember doing this experiment in high school? Raise your hand. Remember, there's this confluence of water, paper, and electricity. You have these water tanks, you have light, you have these things going like this, and you have to trace out the interference patterns. Anyone remember that? You were landlocked, right? Center Reach didn't have water, so, okay. So, here are these cones. Let me bring the cones together. If these were waves, as I drew in the white surface here, if these were waves, they would do this, and you'd get interference, and everybody would be excited. You get slits, double slits, triple slits, all sorts of stuff. But smectics are not waves. I mean, they're mathematically waves, but they're actually things. They're solids. So they crash into each other. Bam, they crash into each other on this line. Why is this line cool? The line is a place where the director changes its direction abruptly, right? You see the cusp? Because of that, the dielectric tensor controlled by the director has a jump in it, and that's what scatters light. That's the focal in focal conic. You see it without any cross polarizers because it scatters light. Where's the conic in focal conic? Well, if you look at the surfaces, you see this red curve. That red curve is a hyperbola. But I wasn't showing you straight lines. We showed you hyperbola and ellipses. So how do you get a hyperbola down here? You have mountains that aren't the same height. If the mountains aren't the same height, then this hyperbola projects down to this hyperbola. Look at that. When two sets of circles crash into each other, they crash into each other on a hyperbola, which is sometimes a straight line. All right? But we understand this completely. To have equally spaced two-dimensional surfaces, I need to have pieces of cone, right? I already showed you that. They have to be pieces of cone. Now I can have different pieces of cone intersecting, and because they have the same slope, when two pieces of cone have the same slope intersect, they always intersect on conic sections. Because they intersect on a plane, and when a plane cuts a cone, you get a conic section. So they always are conic sections. In two dimensions, they have to be pieces of conic sections. And so it made us realize, and now going back to that thing about the speed of light, it made us realize that we've been doing this all wrong. And drawing this thing where I was thinking of this as living in Euclidean space, where this third dimension was a dimension in R3, really I should view these whole things in Minkowski space. Why? I have my coordinate phi, which is the level set coordinate. And look at this equation, minus phi squared plus x squared plus y squared equals 0. Of course, that's the same thing as the equation of a cone. But it's also the light cone condition, or the null condition, in special relativity. And so the cool thing is, as you all remember, Lorentz transformations were designed to preserve light cones. So what happens under a Lorentz transformation to this cone? Anybody? Nothing. It becomes a cone. But what happens to two cones? Look at this. 2 points, space-like separated. at exactly the equal time. You know what's going to happen. Under Lorentz transformation, they're still going to be space-like separated, but now they will be at different times, which means different heights. And their spatial coordinate change, and I make a boost, and bam. You realize this and this are the same texture observed by different observers. And you can say, this doesn't come up. We don't do special smectics, relativistic smectics. But that's not the point. The point is that the Lorentz transformations are just linear transformations. So if I want to study this structure, I can actually use this system and just have a linear change of coordinates. Handy for calculation. All right? There's nothing invariant about the energy. The energy is not Lorentz invariant, but you can make these transformations. And so you can take some fiducial canonical structure and say, I can get everything from there. Of course, I showed you pictures of ellipses. Here is a volcano. See the volcano? The volcano is actually two events that are time-like separated. They're time-like separated. And one of them is a cone pointing up that ends here. The other is a cone pointing down that ends here. They're exactly at the same space point, and they're at two different times. And when I make a Lorentz transformation, both those things change, the space changes, and you get this. And then when I project it, I get my ellipse. And you see, here's one focus. These inside circles are concentric from this focus, and the outside circles are concentric from that focus. And then they intersect on this red curve. It's actually kind of cute. Look at this. I can pick up that whole red ellipse. You see it? And pick it up and rotate it by pi and put it back down. Then, of course, the circles are all continuous, and I've done nothing. You know what that means? All the energy here lies on the red curve, right? Right? This and the old one have this and this have exactly the same bending energy. Because I can pick this red, right? I pick up this ellipse and turn it around 90 degrees, or I can flip it this way, whatever you like. And I can reconstruct all the circles, and they're exactly the same circles, and the only problem now is that there will be a difference on that red curve. So the energy is localized on the focal set. So you have these things. They're all related by boosts. With Ricardo, we discovered, in fact, that there's this extra set of transformations that you don't learn when you learn special relativity. The reason you don't learn them is they mess up causality. But I don't have causality. I have smectics, so it doesn't matter. And so it's OK. And it turns out there's really only one system. You could start with this one. You can use this as your fiducial coordinate system, which is very simple. It's even axially symmetric. And all these other structures are just linear transformations of the original structure. So if you want to calculate energies, it's very convenient. It's convenient to do things in this coordinate system and then write the energy in the boosted coordinate system. Now, I haven't talked much about focal sets and disclinations and dislocations. And part of the reason is I don't know how to put all of those together. Let me show you how disclinations and focal sets talk to each other. Right? Because somehow, in my mind, before we started all this, there were focal conic domains on the one hand, and then there were disclinations and dislocations on the other hand. And I personally never understood how they were all the same thing. But here, let me show you. So here's my minus 1/2, or my plus 1/2 disclination. Here, let me put two of them together. And I'm only giving you the top part. So here's this ridge, it's that ridge, here's that ridge. Here now they're intersecting along this hyperbola, right? And this is a perfectly fine smectic, right? This is the cross-section of an oily streak, right? An oily streak texture. And now let me boost it. I'm allowed to boost it. And when I boost it, I get this. And now I have these cusps. I actually have real cusps in the smectic, right? But the cusps always end on disclinations, right? You could check. If I go back to this thing, look at this. Here, I have one disclination. Here, I have one disclination. And a cusp that ends on itself. Here, I have two disclinations and two disclinations, and two cusps that run off to infinity. The point is, if a cusp either has to be infinitely long, or it has to start and end on a disclination. Right? And then, if you embellish this by remembering how dislocations can end on disclinations, now you're starting to get into a beautiful story of putting it all together. But frankly, I don't know how to, frankly, I don't know how to do it. But maybe somebody here does. So that's kind of nice, and you get this thing, and of course you recognize this as a cross-section of the bend walls that Maurice and Oleg have talked about for many years. This is a side view of it. It's just a boost of the oily streak. So what about 3 dimensions? Because, you know, here we are in 3 dimensions. In 3 dimensions, I can do something dumb. I could just take my system, the 2D system, and I can connect a line through the two along the axis of the ellipse or the axis of the hyperbola and just spin in 3 dimensions. So these surfaces I'm drawing are not surfaces in your head. They're not green surfaces. They're actual surfaces. So here are actual smectic layers. Here I have concentric spheres. Here I have another set of concentric spheres. They intersect on this ellipsoid. These concentric spheres are concentric around the focus of this ellipse, of this focus, and then these are concentric around those, and they intersect on ellipsoids. Or I can do the same thing in 3 dimensions. The problem is that this is energetically costly, because now what I have is I have a situation where I have a smectic, and and there's this whole bad surface that's bad. There's a whole 2-dimensional surface where something's messed up. Can you fix things so that you only have 1-dimensional surfaces because they're smaller? Yes. You can make these Cycloids of Dupin, right? 1810, right? And they've been discovered over and over again. Cayley wrote some beautiful papers on them. Maxwell wrote papers on them, right? And Friedel, I guess, read them all, right? Or at least read one of them, so that he understood that this is a way of getting equally spaced structures. He learned it at school. Okay. It was because they hadn't invented quantum mechanics yet. Right? See how quantum mechanics has set us back, right? Hundreds of years. So here you have these 2 focal curves. They're confocal, like Maurice said. The ellipse goes through the focus of the hyperbola. The hyperbola goes through the focus of the ellipse, like so. You can actually write this very naturally in space-time. And in fact, I have this equation I have to write down, but there's no chalk. Oh, there's chalk. Can I have the lights again, please? Is there some button I can press?
There is.
It's okay, they'll do it. There's a whole... They're listening to me. Hi. Okay, they're doing it. Thank you. So it turns out that Cayley, in 1865, right before Pickett's charge, wrote this equation down. He actually wrote down this complicated, by the way, this coordinate rho is the square root of x squared plus y squared. So I guess he calls this a quartic or a quadric, right? Because it's quadratic in this thing. I don't know what he called it. It was this complicated looking polynomial. It's in this paper, right, in one of his 9 volumes of published work. Z is the z direction, rho is this, s is a parameter, and phi is which layer you're on. Okay? And Cayley wrote this down. He didn't write it down in this factorization. He wrote it down in some complicated way. But what we figured out is that by finding the rest frame of this thing. So by the way, he wrote down this equation for a Cycloid. If you find the rest frame of the Cycloid, you can factor the whole thing into this coordinate, into this structure. And you could say to me, why do I care about factoring it? Go ahead, Vincenzo, say it. I said, why do you care about factoring? Go ahead.
You want me to repeat?
Yeah.
Why do you care about factoring?
Vincenzo asks, why do you care about factoring it? Because look, I've written this thing now. I've written the Cycloid of Dupin as the product of 2 cones. Cones in funny coordinate system. This is sort of radial coordinates, but so what? They're cones. So I know that the Cycloid of Dupin, those concentric Cycloids, are equally spaced. No calculus, just algebra. Because what I've shown you is it's the product of 2 cones. And since a cone gives me equal spacing, the product of 2 cones will also give me equal spacing. Because there's this theorem that if this times this is 0, then one of them is 0. So at least one, both could be 0. And so the point is they're cones. And so you can actually discover or deduce that these seclets give you equally spaced layers without doing any, calculus to do it, which is good because, turning calculus into algebra is, is a fine goal. What button do I press? Lights off. Lights off? No? Ah, perfect. Thank you. So, and of course, here are the pictures. Beautiful pictures of that. Oh, now they're all off. Okay. It's all right. Hold on. Sorry. I pressed lights off. Lights on. Ah, perfect. Okay. And of course, just like the two-dimensional case, the three-dimensional case can be studied in its rest frame where it's nice and simple. So I really need to get to the applied part, right? So I'll whisk through it. The applied part involves this thing called the law of corresponding cones and some really seminal work by Maurice and Jim Sethna, which I relish. It's like a paper I wish I had written. And so here is a section of the focal conic domain, the insides. And I can take this section, see, all right, there's the data, there's the model. This part fits into a cone, okay? Here's the cone. And now what I can do is I can take this cone wedge and substitute a cone wedge from a sphere and swap them out. And because these surfaces come to this cone, perpendicular to the surface of the cone, you can naturally put them into the sphere. And there's no cusp, it just fits smoothly. And so you can take a sphere and you can riddle it with these focal conic domains. The focal conic domains have negative curvature instead of positive curvature, and so it's quite possible that that would be favored depending on your energetics, right? And now the question is, here's multiple focal conic domains. See, here's 4 of them. How do I take 4 of them, right? Here's a beautiful picture of one. Who made this picture? Oleg, are you here? No. Okay. Isn't Oleg one of the organizers? Okay. All right. The answer was yes, he is. So here's another picture of a sphere with the things like that. So what we wanted to do is we wanted to engineer them. We wanted to do the Angevanta part. We wanted to actually do something with them. And of course, there's this beautiful work that we had nothing to do with, but Oleg did, except he's not here. So what you do is you make channels. And you make channels, and what you do is you have these funny boundary conditions. They're not funny. Okay, they're perfectly natural. You have stuff, maybe it's plastic, and the plastic has this boundary condition that the molecules want to lay in the plane of the plastic, which means the layers want to be perpendicular. Right? So here are the layers in the bottom of the plastic, the sides of the plastic, but at the air liquid crystal interface, the molecules want to be perpendicular. So you're just playing with boundary conditions. This is called hybrid anchoring. And you can see that it's natural, if you have this hybrid condition, to actually take a piece of a focal conic. Right? And in fact, they found that if you took a channel like this, you got a whole line of focal conic domains. Like this, if you made the channel wider, there was room for 2 rows, 3 rows, 4 rows. Eventually, you get a nice triangular lattice. All right? If you're interested in that kind of thing. What can you use it for? Well, you can have a whole thing of innies, right? Is there a translation for innies and outies? Is that what they call them in Britain? What do you know what I'm talking about? I'm talking about your umbilic.
Yeah.
It can stick out or stick in. There's no name. Okay, we call them innies and outies. Okay. In high school, that's how when you play boys basketball, you could do shirts and skins, or you could do innies and outies. They separate us a different way, right? So anyhow, here are the. Sorry.
It's hard to find enough outies.
I know. So we always won. All right. So, or you can call it the how you say Pop-Tart texture. Okay. So this is the surface of a Pop-Tart. You can have these innies, but the cool thing is you can have these outies. These outies. So this is sort of the inverse of that. You make this, and then you make a stamp of it. It turns out that this is very precise, and you actually get 300 nanometer dots. That's very small, right? In units of meters, that's very small. And nanometer, anything nano is cool, 300 nanometers. So let's say you're making extremely sharp, precise features which is good if you want to make small things. The layer spacing. I mean, it has to do with the layers are much smaller. So it has to do sort of with Vincenzo's question about the penetration depth, right? The bend penetration depth. So there's, if it were perfect, you would get down to the molecule size, but it spreads a little bit, but it still doesn't spread that much.
So it's basically the bend penetration depth up to some numerical factor.
That's always true.
Constant numerical.
Yeah. Okay. All right. Oh, he said, so it's the bend penetration depth up to a numerical factor. And I said, that's always true. He said, a constant numerical factor. You can use this to make microlens arrays. So if you like the letter F, you can copy it many times with his lenses. And then you can use it to capture colloids, because colloids like to go where defects are. And then my favorite one is that you can make super hydrophobic surfaces. You see, if you put a drop of water on this, it touches this thing at every contact angle between, right, the drop of water touches it when it's like this and like this. And so by treating it properly, you can make surfaces. This is a way of making a surface that water, just falls off of, right? Look, it beads, okay. So we wanted to control this a little further. In particular, who needs triangular lattices? We wanted other kinds of lattices. We wanted square lattices. And so what we decided to do is we tried to make an array of posts, microposts. And it turns out that if you have microposts and they have the same plastic boundary conditions, they will actually pin and anchor these focal conic domains. If the liquid crystal is shorter than the post, it'll make a focal conic domain in the center. And if they're taller, it'll make one that sits on the tops. And we did, right, so here's the same molecule. And we verified that we get a triangular lattice if we leave them alone. But then we put them on these microposts. Here is the overfilled case where you get this pattern, now a square pattern. Not only is it square instead of triangular, it's the wrong spacing. Left to itself, it would have 30 micron-ish spacing. We put our posts much closer together, see, 2 or 3 microns. So we can actually take over. We can tell those focal conic domains where to sit. Right? This is strong enough to let them sit. And of course, the taller we make the post, the better it is. There's a bigger surface area that's telling them where to sit. We can also do it where we underfill them. Here's something cute. If I go back to the overfilled case. All right, if you have really good eyes, you'll see that between the squares, so here's the squares from the tops of the posts, there's actually a teeny little dot coming from between the posts. So you're starting to get the other ones also. Okay? What to me is especially interesting is that you can make 10 micron posts, and as far as we know, as far as we've gone, you can actually fill it up to 40 microns, and you still get the pattern on the top. It's like the princess and the pea. Do they tell that story? Right? You can still feel the posts, You have all these blankets and all these mattresses, right? All these layers, right? And the layers can distort and do all those things, but you can still feel the posts underneath. And then we wanted to know, could we do something even sexier? Could we put, instead of toric focal conic domains, could we have the bent ones? And really, this is all the brilliance of Dan Beller, who is traveling. He's not absolved. What is it you get? What is that thing you get? An indulgence. We grant him indulgence for traveling. You actually can take posts, and the posts are quite large. And because of that, they're short, so their pinning isn't as strong. Do you see the 4 dots? So instead of having one focal conic domain per post, you get multiple focal conic domains per post. And of course, now you've broken the symmetry when you have 4 of them. And I already showed you a picture, right, of what happens. So here's the idea. Here are the 4. They actually come together and they tilt in a little bit. They actually, instead of being straight up and being toroidal, focal conic domains, they tilt in. They actually get a bit of a hyperbolic line. And we can actually test this numerically. So you get this sort of the superlattice of these things tilted in. So here's Dan's rendition. Here's the single focal conic domain inserted in a sphere. Here are 4 of them. But look what terrible happens. Are you ready? You know what's going to happen? I have one set of 4 and another set of 4. Now they intersect on a surface. Everything we've been doing so far has been to avoid intersecting on surfaces. We wanted to have curves. But Dan's brilliant observation was, if it's a thin film, those surfaces could be outside the sample. You don't have to, right? It's true that if you had an infinite system, the surfaces would be inside the sample and that would be costly. But if it's a thin film, I can arrange things so that where they would intersect is not inside the surface. These are virtual walls. So they don't cost you any energy because you don't have to count them, right? And so he made a construction that does not rely upon the standard law of corresponding cones, which was designed to make sure that you never got surfaces where the energy, where there was a cusp. But his structure gives you surfaces outside, above the sample and below the sample. And it actually, he makes a model of it. So if you like, we take a cut, a diagonal cut along this line. So we're looking at the surface. So we use AFM to measure the height of the surface. Here are the cones. So here's a pair of purple cones. They're pointing in a little bit. And here's his surface. So here is the focal conic domain part, the black part, and he connects them with pieces, arcs of circles. He minimizes the energy. The energy is reasonably lower. All the surfaces where they would be forced to intersect are up above the sample. Eventually, these spheres will crash into each other, but up above the sample, so I don't have to worry about it. And you can plot, I don't have it, but oh yeah, here it is. This is the model. This is the data. All right, and it's not just qualitative, it's quantitative. You can actually check. So using his surface model, which is not the law of corresponding cones, we can actually reproduce the data. And now we have this way, we have a new set of rules. If we have thin films, we can engineer things differently. We're not constrained by the law of corresponding cones. So I should credit everybody who did this. So 3 of them are here now. Dan's on his way. Marcelo Cavallaro works for Gore. You know, Gore. It's cool, right? They're in Delaware. And Apurity, Hongawan's off to a university in Thailand, I don't know how to pronounce it, Mahidol University. But she and Marcello did all the beautiful experiments. They really got exquisite control of not just the liquid crystal, but they also got exquisite control of the anchoring. That was the most important thing, is to know that the anchoring is what we say it is. Right? And they were able to do that, and Purity could do the AFM. And then I told you about Dan's work, and Brian, Sabetta, and Gareth were instrumental in us understanding things like this. And then I have 2 grown-up collaborators, Kate Stebby and Shu Yang. And this was supported by NSF. And thank you for your attention.
Thank you, Randy, for a wonderful development of the pure and the applied. Fabulous. Questions? Yes.
Randy, I was fascinated by your description of the changing texture as mediated by the transformation of special relativity. Can I understand?
Did you say captivated?
Yeah.
Okay. I have to repeat the question. I'm just
If you don't want Randy to repeat the question for you, then you're speaking to this mic.
But then I can't mock him.
Hi. So I would like to provoke you to think about equidistant smectic layer on a curved surface.
Yes.
In the same line.
Yes, I've written papers with you on this.
Yeah, I know that.
Okay.
But I don't think.
Now
that,
they know that.
But I don't think that there's an understanding in terms of this construction that I have, at least. Namely,
oh,
I would like to
no.
ask you if you take a wall here and there is equidistant and straight layers, then you have a bump, and that deforms the geometry of the layer and makes a grain boundary on the other hand.
Yeah,
How
so
do I understand this sequence in terms of your transformation of special relativity?
well, of course, the transformations in special relativity require that the structure I'm talking about is Lorentz invariant. And as soon as I have something on an arbitrarily curved surface, I lose Lorentz invariance. I have local Lorentz invariance, but I was doing global transformations. However, there are 2 other spaces that are homogeneous, and you can do everything on de Sitter space and anti-de Sitter space, if you like. And it turns out anti-de Sitter space is a natural place to study smectics on spheres instead of smectics on flat surfaces. And then you can recapitulate all those things, and it turns out all the different focal sets you can have on a sphere are actually related by, it's not a Lorentz transformation, but it's the moral equivalent of the Lorentz transformations. It's a mess. You can't do anything. I mean, you can do some things, but not very many things. But you could go back to somebody's, what is it, Gareth? There's the 11 almost homogeneous manifolds, you know what I'm talking about? You can certainly talk, so there's the completely homogeneous isotropic manifolds, but then you can have ones with reduced symmetry. You could have something which has symmetry, like boosts in 2 directions and not all 3. And then you can imagine trying to make those structures, and they will have transformations amongst themselves also. Thank you, Gareth.
Any more questions? Well, if not, thank you very much. Thank you. Wonderful.
Thank you.